All right, in section 2.2, we are going to talk about graphs of functions. So our goal here is to learn the details for visualizing a function graphically. Now we're going to start out with some definitions. If f is a function with domain A, then the graph of f is the set of ordered pairs, the set of all x comma f of x. It's an ordered pair such that x belongs to the set A. The graph of f is a set of ordered pairs that's plotted in a coordinate plane. In other words, the graph of f is the set of all points x, y, such that y is equal to f of x. That is, the graph of f is the graph of the equation y equals f of x. A linear function is a function f of the form f of x equals mx plus b, which represents a line with slope m and y-intercept b. A constant function is a function f of the form f of x equals b, which represents a horizontal line with slope m equals 0, and it has the equation y equals b. So for example, if we want to plot y equals 3, the line y equals 3, notice that it doesn't matter what x value you choose, y will always be 3. Okay? Now, if we want a linear function, this is an example of a linear function, x plus 1. Okay? So, we have that as an example. Now, functions of the form f of x equals x to the n are called power functions. They are called power functions. And functions of the form f of x equals x raised to the 1 over n are called root functions. Now what we're going to do is we're going to sketch the graphs of the following functions. F of x equals x squared. You may already remember the shape of this graph, but let's plot a few points and then plot them over here and sketch the graph. So when x is 0, you substitute 0 in here and you get 0. When x is plus or minus 1/2, you get plus or minus 1/2 quantity squared, which gives you 1/4. Let's zoom in a little bit more. Okay, and when you substitute in, you substitute in plus or minus 1, you get 1. Substitute in plus or minus 2. Remember, you're substituting it in here. You get 4, and so on. So notice that your graph, when you plot it, is going to be we can make it a better one. How about that? We'll make it a little bit better. You get this parabola. So you'll have the point 1, 1 here, and then you'll have the point -1, 1 there, and so on. Okay? So the graph of x squared is a parabola. Now, the graph of f of x equals x cubed, same thing. Plot some points. So use a t-chart. When x is 0, y is 0, meaning you substitute your x values in there. When you get 1/2, x is 1/2, you get 1/2 cubed, which gives you 1/8. Then when you substitute x equals 1, you get f of x is 1. 1 cubed is 1. When you substitute in 2, you get 2 cubed, which is 8. You substitute in negative 1/2, you get negative 1/2 cubed, or negative 1/8. And then you can plot your points, and as you plot your points, what you'll find out is your graph is going to look like so. Okay? So for example, you have 2, you'll have 8 up here, so 2, 8, and then negative 2, negative 2, negative 8. Okay? All right. So those are examples of power functions. Another function is the square root of x. The square root of x is called a root function because you can rewrite it as x to the 1/2, where your 1 comes from there and your 2 comes from your index. Okay? So, again, choose various x values, substitute it in for x here. The square root of 0 is 0. The square root of 1 is 1. When x is 2, the square root of 2 is what it is. When x is 3, you get the square root of 3. When x is 4, you get the square root of 4, which is 2, and so on. And then you graph it. That's your graph. Okay? So, now you know what power functions and root functions look like. Okay? Now, you can take out your calculators because the next problem is a calculator problem. So now what you should do is take your function and your graphing calculator, and where you have graph, you type or press graph and you're able to enter the function x squared minus x minus 20, and then hit graph. Okay? What you should do, what you should get a function that looks like a stretched parabola, and the x-intercepts are negative 4, 0, and 5, 0. The y-intercept is 0, negative 20. Negative 20. And you will get, that is your graph. Okay? Now, what you should do, scale your window. Look at your window, and then you can go from negative 7 to 7 for your x values, and then do that by negative 25 to 20 for your y values, and then you'll be able to see the graph more accurately in your window whenever you sketch it on your calculators. Notice that in your homework problems, you'll have different intervals given, and it'll tell you to choose the most appropriate one. You choose the most appropriate one by which one gives you the better view of your graph, okay? The most accurate part. Now we want to sketch a graph of the following piecewise defined functions. A, we have f of x is equal to the absolute value of x. The absolute value of x is equal to x if x is greater than or equal to 0, and it's negative x if x is less than 0. So this means that we have x if x is greater than or equal to 0. So we have 0 on up here. Okay, so we have this diagonal line here on the right of the y-axis, and then we have negative x if x is less than 0, which means now we have an open circle going this way on the left of the y-axis. But it's already closed here, so that just means we include it. So this combined gives us the absolute value of x. That's the graph. Okay? Now we want to, in part B, graph the function f of x equals 2x plus 3 if x is less than negative 1, and 3 minus x if x is greater than or equal to negative 1. So we need to figure out what happens, or what's the shape of the graph. We know this is a line and this is a line, but we need to figure out what our points are. So let's do an aside. So note that here we have if x is less than negative 1. So if x is less than negative 1, let's figure out what the x-intercept will be. So we have, to find the x-intercept, you set y equal to 0. So that means 0 is equal to 2x plus 3, which means 2x equals negative 3. We subtract 3 from both sides. And now we divide both sides by 2, so you get x is negative 3 halves. Now, if we substitute in negative 1 here, then that would give us 2 times negative 1 plus 3 is negative 2 plus 3, or 1. But because this is strictly less than, we have an open circle at 1. So graphically, we would have 1 here. I'm going to move this up, zoom in a little bit so we can make it a little bit more visible. So we'd have an open circle at the point 1, 1, and then that's negative 1, negative 1, 1, okay? And then you would have an x-intercept of negative 3 halves. So that point here is, let's not use an arrow because I don't want you to think that's a part of the graph. So this is negative 3 halves there, okay? Now, we got the first part, so yay, we got the first part. Now, the second part says we have 3 minus x if x is greater than or equal to negative 1. So again, let's figure out what happens there. So 0 is equal to 3 minus x, or in other words, x is equal to 3. And so that means that we have 0, 3 is on the graph. So that point here would be 3. And then what we then have to find is we have to substitute a negative 1 here, a negative 1 over there. And then that would give us 3 minus negative 1 equals 3 plus 1, or 4. So that means whenever x is negative 1, y is 4. So we'd have negative 1, 4 up here, and then we would have 3 here, and that's the graph. Okay, so make sure you go through the homework and know how to graph piecewise defined functions. You'll have to be able to sketch those as well. Another common example of a piecewise defined function is that of the greatest integer function. Okay, the greatest integer function. Okay, the greatest integer function has the symbol here, and it's called the greatest integer function, and it's defined as the greatest integer less than or equal to x. Less than or equal to x. For example, the greatest integer less than or equal to 2 is 2. The greatest integer less than or equal to 2.3 is 2. The greatest integer less than or equal to 1.999 is 1. You're choosing the smallest, the greatest smallest integer less than or equal to the number inside of the symbol. So the greatest integer less than or equal to 0.002 is 0. The greatest integer less than or equal to negative 2.5 is negative 3, right? Because negative 3 is the smallest integer greater than or equal to this. Then the greatest integer less than or equal to negative 0.5 is negative 1. So we're going to graph this by, first let's recognize some things over here. So when x is greater than or equal to negative 2, but strictly less than negative 1, the greatest integer there would be, the greatest integer less than or equal to x would be negative 2. Choose the smaller one. The x greater than or equal to negative 1, but less than 0, the greatest integer less than or equal to x in that case would be the smallest one, which is negative 1. For x greater than or equal to 0, but less than 1, you get 0. And here you get 1, and so on. So notice that we should, when we graph this, have a closed circle at negative 2, open circle at negative 1 when x is between negative 2 and negative 1. Graphically, that means, so let's graph 1, 2, negative 1, negative 2, and then we'll have negative 1, negative 2, 1, and 2. And so when x is between negative 2 and negative 1, we have a closed circle here at negative 2. But then it's an open circle there at negative 1 when x is negative 1. Then whenever we have x is between negative 1 and 0, so now x is here, we get y is negative 1, but this corresponds to y being negative 1. So that means we have a closed circle here, open circle here, and then for this part, we have x is between 0 and 1, closed circle is 0, everything in between, open circle at 1. And then here, we have a closed circle here, everything in between, and open circle there. Okay? Then this means we just continue. Okay? So that's the greatest integer function. And then the other concept we need to talk about here is that of the vertical line test. Notice that a curve in the coordinate plane, random mark, let's take that off. A curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once. So if we take a vertical line, suppose we have a vertical line here, and we take this vertical line and we move this vertical line across here. Does it touch this curve in more than one point? No, it does not. So that means that this passes the vertical line test. And we get that this example is a function. It passes the vertical line test, VLT for vertical line test. But what happens if you take a vertical line here? Well, it intersects the graph in 2 points. So this would not be a function, right? It does not pass the vertical line test. Now, in order to determine if an equation represents a function, this is the process you take. You solve the equation for y, and then determine if the resulting equation defines a rule or function that gives one value of y for each value of x. Does, for example 6, does the equation define y as a function of x? So, what we have to do here, we have to isolate y and put it in terms of x and find out whether or not it gives us a function or defines a function. So let's isolate y. Well, subtract x squared from both sides. That gives us y squared equals 9 minus x squared. Or now we take the square root of both sides. And that gives us y is equal to, remember when you take the square root, you get plus or minus. So this is plus or minus the square root of 9 minus x squared. So because you get two possible answers here, so that means that for each x value, you have two possible y values. What does that mean? It's not a function, right? So the answer is no, this equation does not define a function because for each x value, there are two y values. Okay? And you can look in your book for examples that tell you, okay, this equation does define a function. Okay? Now, one last thing to end with. On page 166 of your book, there are some graphs of basic functions, including linear functions, power functions, root functions, reciprocal functions, the absolute value function, and the greatest integer function. You need to make sure you know all of these. You will be required to tell me which graphs represent which functions. Okay? Have a good one. See you soon.